So let's continue our discussion with what happens if you kind of use your pointer to write more data than what's required. And that's also like always a bad idea. Okay, so to set up our example, we have P here, we have the heap here, and let's say we asked for some 1024 bytes or 1 KB, and as we discussed, we'll actually, 4 bytes here would store the number 1024 just as one of the potential implementations of the heap allocator. Okay, let me get rid of this and say this is the 1 KB region that we are pointing to, and this address right here um, happens to be ABCD in hex. So this then is ABCD, and the allocation, the syntax might look something like so. Let me make it a character pointer for easy math. And let's say we do 1024, right? All of this is good. It's great. We got 1 KB. We got, heap allocator kept 4 bytes aside before the start of the allocated region and stored 1024. Let's just say we also did, let's say char q. Hypothetical scenario can happen. Uh, and let's say we also asked 1024, right? So then we have 1024 saved here in 4 bytes. And then again, we have 1 KB allocated to us. And let's say this is, I don't know, beef for whatever reason, let's just assume. And Q somewhere is Q, and Q is holding beef, right? Okay, great, perfect. Now recall that if we did this, so P would start from A, B, C, D, and we would have added 1024, right? So essentially, we are now pointing here. So from 0 to 1023, those are the bytes we are allowed to touch, meaning the first byte here, second byte here, blah, 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 the 10 to third byte. That is the 1024 total bytes, including, right? So 1024 total bytes that we are supposed to touch because we asked for 1 KB allocation. Let's just say what we do is we dereference this and write the number. Uh, okay, let's say we write the number -1 there, right? So there were 4 bytes here as an int that we're storing 1024 because malloc takes a size underscore t, which is an int, which is 4 bytes. And what I'm saying is the top of that, so these are the 4 bytes. And maybe to represent 1024, we only needed 2 bytes here, so these were 0. But what I'm saying is, because of this math here, the pointer incremented, a character pointer incremented by 1024, then dereferenced, and we write like a -1 there, but -1 is nothing but 255 in the character line. Or, well, let's not, complicate our life. Let's just say we write like a 1, right? So in this byte now, we have gone and written 1. So the 32 bits that represent an integer here. So 1024 was saved in like the early 16 bits, and we wrote like a 1 here on some whatever 31st down to that would be like what, 24th bit maybe. Do the math. So 24th bit is set, and all of a sudden this entire integer is way higher than 1024, right? If you're following so far, see what happens. First off, we ended up using P to go to a region that was not owned by P, and nobody puts a check on that, right? Well, if you overshoot P by such a margin that you're going in forbidden region of the memory that is guarded by the operating system, then yes, your program will fail. But if you're doing something like so, something that's like very subtle, not too off, off by one kind of, or let's say we wrote into 1025, which is the byte here, and wrote like a 1 here, even then this number is way bigger than 1024. And that is the key, that number changing can lead to a mess. Let's say after a lot of time we freed P. So this memory region is gone. It's reclaimed by the heap allocator or memory allocator. Later we do free Q. And the way malloc works, the mechanism of it, we talked that okay, beef would be passed as an address. It'll step back 4 bytes and then it'll say, okay, what's the number stored here? Oh, the number is not 1 KB. It's maybe 512 KB. Some weird number, right? Some big number. And now it will go ahead and instead of freeing 1 KB, it'll actually free a lot more. And the problem again is that the later memory region might be in use or claimed by some other pointer. So again, this kind of a behavior of pointer or using region slightly beyond the allocated region can lead to a mess also. And there are no runtime checks on all of this. So this can also lead to catastrophic behaviors. And hopefully now you're starting to get on board with why dynamic memory allocation and freeing it, essentially one has to be like very very careful around it. And this is why there are a lot of bugs when someone writes like code in C, typically systems level code in C, because small code, it's still tiny code, small programs, it's still all right. As you go write bigger and bigger software, uh, it's very easy to allocate memory, not free it, double free it, allocate and overshoot. All of that is possible, and these are very hard to catch by automated tools.